We've been talking about finding the zeros of high-ordered polynomials in the nth degree. Particularly, much of this discussion is around the rational zeros theorem and using synthetic division in order to find all the potential rational real zeros. Since there are also irrational zeros and complex roots making up all the possibilities mentioned in the fundamental theorem of algebra, we are now talking about other rules and theorems that exist in this topic. So one such rule is developed by René Descartes and is therefore titled Descartes' Rule of Signs. It says if f is a polynomial of nth degree and real coefficients and a sub 0 is a non-zero constant, then we can look at a polynomial and say, 1, the number of positive real zeros of f is either equal to the number of variations in sign of f or less than that number by an even integer. And we'll explain that in a little bit. The second rule is the number of negative real zeros of f is either positive or is either equal to the number of variations in sign of f of negative x or less than that number by an even integer. So let's take a look at this example then and how they're using it. They're saying use Descartes' rule of signs to describe the possible real zeros of this polynomial. So here's this polynomial, and here's what they're talking about as far as the changes of signs. So as we just walk from left to right on this polynomial and note that this first term is positive and the second term is negative, then that's one sign change. If we go from that term into the next term and see that the sign has changed again, that's the second sign change. And then this sign has changed to negative, and so there are 3 sign changes. So, since there is the possibility of, for real roots, there's positive, and then there's negative, and then there's complex, and that really makes up all the possible roots of a polynomial, then what we've said here, according to Descartes' rule of signs, is that there are 3 or 1, because we can only decrease by an even number until we get down or near to 0, possible real roots that are positive. So if that's the case, and we're a third degree polynomial, then we've pretty much used up all the possibles. And so there are going to not be any negatives, and there are not going to be any complex. Or, in this case here, we might have negatives or complex. So now, in order to determine whether we have negative or complex, we have to use the test now for negatives, which is the second test. F negative x is equal to, and if I say negative x, notice what that's going to do to the sign of the first term. Since that's to the third power, negative x to the third power is negative x to the third. So that first term then becomes negative 3x to the third. Notice the second term is an even exponent, so negative x squared, negative x squared becomes positive x squared because negative times negative is positive. So in this case right here, this one started out with negative 5, and then we had negative negative, so that's positive x squared, so that's just positive x squared. So that one really didn't change because of the even exponent. The next one, negative x becomes negative x, and so we have negative 6x. And then minus 4. Now let's look at how many sign changes there are in this polynomial. Negative to negative, no sign change. Negative to negative, no sign change. Negative to negative, no sign change. So there are no negative real roots or zeros. And that means then, if we are going to pay attention to the possible real roots or all the possible roots, then the fundamental theorem of algebra says that I must have 2 complex roots, and those are going to be complex conjugates. All right, let's take a look at this again and say that let's work on this particular problem that I pulled out of the homework set. So here's h of x, and notice we're just going to go ahead and do the positive, negative, and complex. We're going to do the first test. We're just going to look at our polynomial and see if there's a sign change. So here's one, and then here's another one, and then there's no sign changes beyond that. So there are two possible positive zeros then that are real, or there are none at all. Now, so let's take a look at the possible negative zeros. So we're going to do this, and we're going to do that same routine. So x to the fourth, that ends up being negative times negative times negative times negative. That's still a positive. So that doesn't change this at all. 2x to the fourth, even though I'm using negative x's, works that way. And then negative x times a negative 3 is going to give a positive 3x, and then plus 2. Now let's count our sign changes. There are no sign changes because this is positive to positive, positive to positive, so no sign change. And so there are no sign changes, and so there are no negative roots. There are four, the n is 4 in this case, so there are 4 possible roots. So that means for the first case, 2 of them could be positive, and that would leave 2 more in the complex to make a complex conjugate set. And then since we still know that there are no negatives, then we could say that there are 4 complex and maybe 2 pair then of complex conjugates. So that's for h of x. Let's check this next f of x out and do a test. So from the first to the second, no sign change. From the second to the third, no sign change. From the third to the fourth, there's no sign change. So we pretty much have determined then for positive, negative, and complex that there are no positive roots. So let's check f of negative x. Let's see, that's going to be a negative 3x to the third, positive 2x squared, and negative x plus 3. How many sign changes? 1, 2, 3. Oh, okay, so now we have 3 possible negatives, and we can decrease that by an even number, so we can decrease that to 1. There's never going to be any positives, so we've got the case now where we have 3 total. So if we have 3 total in the negative, then there's not going to be any complex in that first case. The next case would be, let's say that there's only 1 negative, and then that means that we're going to find complex conjugate. And so there's 1 plus 2 is 3 possible roots. So that's Rene Descartes' rule of signs. And it can be used to determine, some of the possibilities and kind of narrow things down in our search for zeros of polynomials.